Lesson 5.1.1 part, or day 2.
Day 2.
Okay, so yesterday we had all of those lovely identities on the front page that we learned. Is it emergency?
No.
Can it wait then?
Yep.
So just start this. Thank you. Okay, so we had all those identities we learned yesterday, right? You're going to be wanting to flip back and forth probably today. Not ideal, but, be flipping back and forth. And we looked at, how to answer some specific questions, how to find specific items. Today, our job is all about simplifying, okay? If they give us, you can see A, B, and C right there. You have D, E, and F. And we're not going to get all 6 of these done. We're going to do a handful and then see how time is going. But the idea is to simplify these. These expressions can clean up into something simpler. A lot of our expressions go from what you see there to one trig function. Okay, or maybe a trig function squared. Or, on the high end, maybe it's a trig function plus 1. Or, it cleans up to be a lot nicer than what you see there. So now, what you see at the top are 5, I don't know that I want to call them steps, because you don't do all 5 steps every time, but they are 5 tips or steps to consider, okay? Because we don't even necessarily do them in order, but they're kind of like 5 starting places, things to consider that we could possibly do to simplify these problems, okay? So don't be expecting, oh my gosh, I have to do 5 steps every time. No. Okay, so some of those steps include create common denominators to combine fractions. Obviously, that one can only work if there are more than one fraction being added or subtracted, right? So that's not something you'll do every time. But if you see fractions being added or subtracted, getting them to one fraction will be a good starting point. Item number 2, separate numerators by dividing each piece by the denominator. So that could be taking one fraction and doing just the opposite and splitting it into 2. Okay? Possibility number 3 is to factor or FOIL something. So factoring could be looking for a GCF. FOILing would be taking like a binomial times a binomial and multiplying them together. Item 4, look for a Pythagorean identity. You remember those 3 Pythagorean identities we looked for yesterday? Where it was a function squared plus 1 or a function squared plus function squared. Those can be subbed out, right? Like if you see a sine squared x plus cosine squared x, if you recall from yesterday, that equals 1. So you could take that out and replace it with what it equals. Okay, so we'll be looking for Pythagorean identities. And then the 5th item to consider is changing all trig functions to sine and cosine. Every trig function can be written in terms of sine and or cosine. All of them, if you think about it. And so an option would be to take them all, put them all in terms of sine and cosine, and see what kind of canceling happens. Okay, kind of see what happens there. So those, again, they're not 5 steps we're always going to do. They're just 5 things to consider when trying to simplify a problem. Okay? So, looking at example A, the directions are just simplify. So we have sine cubed x plus sine x cosine squared x. And the obvious thing, why can't we add these as is? Yeah, they're not like terms, are they? If this was sine cubed x plus sine cubed x, that's like terms, add them. Okay, but this is a sine cubed x and a sine x cosine squared x. So those are different pieces, so we can't add them. Take a glance at some of the pieces you see above, or some of the 5 possibilities. Start kind of going through them in your mind. I mean, for instance, can we rule out number 1? Number 1 says to combine fractions. I don't even have fractions here, right? So probably not, the best thing to consider. What do you see? Okay. Both terms. There's 2 terms being added, yes. And they both have a sine x. Sine x is what we would call a GCF. Does this sound familiar? So on example A, we're going to start by factoring out a GCF. And so that in orange is just me kind of, okay, like that's the quote step I'm doing there. So what do both terms have in common? Is it just a sine x?
No, yeah.
Yeah, this one has sine cubed, so this one has 3 of them, but this one only has a sine x. So we're going to factor out a GCF of sine x. And realize a lot of these terms are in terms of x. Our identities were in terms of theta. That's just a different variable, right? X, y, theta, all just different variables. So if I factor out my GCF of sine x, then think about dividing each of those terms by sine x. If I had sine cubed x, and I divide away a sine x, what's left? Sine squared x. Plus, if I had sine x cosine squared x, I divide away a sine x, what remains? Cosine squared x.
How can we keep the x on the sine squared
X
x?
goes with, you can't write sine without a variable.
Oh, okay.
You cannot write a trig function, any of them, without a variable. There has to be a variable on there. That is part of it. That is attached to it. And just FYI, you can't divide sine and x apart of sine x. They are stuck together. Okay? Okay, so there's one simplifying step. Here's where I would go back. I mean, if you see something, great. If not, go back and reassess your 5 original thoughts of ways we can simplify.
Oh. So here's the Pythagorean.
Oh, yeah.
Okay, so I see squared trig functions being added. And if we go back and flip back to the previous page, anytime I see squared trig functions being added, subtracted, those kind of things, I'm thinking I better check my Pythagorean identity. Does this right here match up with one of my Pythagorean identities?
Yes.
It's identical, yes? Okay, sometimes they'll be in slightly different forms, so we might have to work with them, but this one's identical. Sine squared plus x plus cosine squared x is going to be equal to what? 1. So I could take this whole expression and replace it with a 1. And I'm going to just kind of write out here, in case you go back and you're looking at this later and thinking, how did we do that? We just used a Pythagorean identity. So now, in my parentheses, instead of having sine squared x plus cosine squared x, I have a 1. Outside my parentheses, I still have sine x. Okay, tough math here. Sine x times 1. Sine x. And I jokingly say tough math, but as some of you are saying, I really didn't know that. It's still basic math. What happens when you multiply something by 1? It stays the same, right? So, don't take this too difficult here. Okay, we're down to sine x. Guess what? We're done. Okay, you're down to a trig function. There's probably not anything you can do here. But is sine x more simplified than sine cubed x plus sine x cosine squared x? Very much so, yeah. Okay, questions I can answer about that one. Okay, well, let's try B. And as we go through these, I will tell you, I'm going to go with what I know, what I see, what you guys see. On some of these, there is one and only one way to do them. On some of these, there's definitely more than one way to do these and still get it correct. So just, And with that being said, there's also wrong ways to do things, though, too. Works both ways. Okay, so B. Secant x plus 1 times secant x minus 1 over sine squared x. You got a thought or a question?
I guess
Okay. 2 parentheses. Both binomials. Let's FOIL. Now, as you FOIL here, what do you notice about these two parentheses?
Plus one and negative one. That's what I know.
Okay, the plus one minus one, what'd you say, Ross? Okay, yeah, the vocabulary word is they're conjugates of each other because of the plus one minus one, because they're the same thing, but they have opposite signs. What's going to happen when we multiply these? The what cancel? The middle terms, right? In FOIL, the outside and inside cancel. So you really only have to do first and last as long as you know that's true. So, secant x times secant x, secant squared x. And traditionally, when we write that, we write secant squared x, and we put the second right there between the secant and the x. The other way you could write that is to say secant x with parentheses, quantity squared, just for your reference. Those are equivalent. What you cannot do is just say secant x squared without parentheses, because that would be the secant of x squared instead of secant squared, instead of the whole thing being squared. Okay? So just some small tips there. Okay. Sorry, I'm interrupting myself. Secant x times secant x. Officially, double check ourselves. Secant x times minus 1 is going to be minus secant x. 1 times positive secant x is going to be plus secant x, so those will cancel. 1 times minus 1. Minus 1. Over our denominator of sine squared x. Do me a favor, write that down every step of the way. Don't kind of think, oh, I'll come back and put that on later. That could run into problems. Okay. We're not done. We can have a secant in there for right now. I mean, one of our options is to change everything to sine and cosine. I think that would make it uglier before it got prettier, though, in this case. Yeah, but secant squared over sine squared wouldn't be very pretty. I mean, and that's the thing. You guys are coming up with ideas. Let's investigate that question. Can we use an identity? What'd you say? No? No? And that would be going with Shively's idea of changing secant, everything to sine and cosine. Here's my hint, if you guys are ready for it. When I see squared functions being added or subtracted to other squared functions or ones, I tend to investigate my Pythagorean identities. So what is the Pythagorean identity that uses secant and 1? Officially it reads 1 plus tangent squared theta equals secant squared theta, correct? That's kind of my side note for the moment. That's officially what it says. Use your algebra skills. What can I do if I use algebra skills here? Yeah, right here I have a secant squared minus 1. Could I make this a secant squared minus 1? Yeah, there's a positive 1 here, so I can subtract 1. If I subtract 1 there, subtract 1 there, and so now we have just rearranged this to write that tangent squared theta is equal to, secant squared theta minus 1.
Okay, so it's tangent squared theta over sine squared theta.
Okay, so We rearrange that. We know that tangent squared of some variable, I use theta because that was what it was in our identities. Tangent squared is equal to secant squared minus 1. What do I have in the numerator right here? Secant squared minus 1, yes? So what can secant squared x minus 1 be replaced with? Tangent squared x. So we can use Pythagorean identity to rewrite the numerator as tangent squared x. My denominator is still sine squared x. And if you want notes for yourself later to go back and say, how did you do that? That was a Pythagorean identity. So again, squared functions, add or subtracted to other squared functions, or add or subtracted to 1, make me think to do something like that. Okay, we're getting closer. It's a little cleaner each step we go. I would say we could go a little farther though.
Oh yeah, we get the square root of the whole.
It's not an equation, so I can't square root. Because in order to square root, that's one of the things that you have to do to the left and the right. So you can't square root an expression, is what I'm saying.
I got it. I was thinking multiply by the denominator maybe. So
Okay, I'm still trying to process Jason's. We can't multiply by something because again, we don't have an equation. Okay. Are you asking Jace or me? Okay, so what do we know about tangent according to a quotient identity? Tangent is sine over cosine. So yes, it then follows that tangent squared is sine squared over cosine squared. Now, we're going to have a fraction within a fraction there. However, here's my thought on that one. And you can do this before or after, but this is a fraction, right? What does a fraction really mean? It's division, right? So if and whether you do this now or later, it's tangent squared x divided by sine squared x, right? But what did you guys just talk about with tangent? Tangent squared is going to be sine squared x over cosine squared x. What did I just use to get from there to there? Yes, I can. Assuming I'm going off the screen is what you're telling me. Not quite there, but yes. Okay, so tangent squared x, because tangent is sine over cosine, then tangent squared is sine squared over cosine squared. How do we divide when we get fractions involved? Yeah, you flip that second fraction. Officially, my wording is multiply by the reciprocal. Now, I don't want you to go identity or fancy or anything. Just what's the reciprocal of sine squared? If sine squared is sine squared over 1, then the reciprocal is 1 over sine squared x. And I'm not saying what's the reciprocal, like change that sign to something else, because what's going to happen now that we have these fractions? Sine squareds cancel. When I multiply this, I currently have 1 on top, 1 over cosine squared x, which is pretty simple. However, you won't see them leave a fraction unnecessarily. So this is when I would use the reciprocal and flip from 1 over cosine squared to secant squared x. And that was a reciprocal identity that allows me to do that.
So what happened to
Just a second, Levi. Shelby, you got a question or did you have an answer that I missed? It was not. No. No. Nope. We can because... Okay, so Shelby's question is, was tangent squared over sine squared not the final answer? Okay, so you guys can understand my explanation. And because I know there's a sign within tangent, I want to investigate that farther. And when I investigated that farther, we found that signs can cancel. And so, yes, we did need to continue there. I wasn't continuing just for fun. It was necessary. Okay.
So what happened
Okay, so what happened to tangent squared x?
You made it into sine squared x over cosine.
We used our quotient identity, say sine squared x over cosine squared x. Yep. And then fractions became involved. In order to divide fractions, we know from our middle school days, you multiply by the reciprocal or keep, change, flip. And when you flip sine squared over 1, it becomes 1 over sine squared. Sine squareds cancel. 1 over cosine squared. And we know that when cosine's in the denominator, that's the same as a secant squared. Okay. Where are we at here? There were a lot of parts on that one. And I mean, that's the thing. You're going to have ones like the A where there weren't a lot of steps. You're going to have ones like B where it's going to take you a few steps to make progress. And this is one of those things. Some of you it's going to take some of you guys a while to see this all. And some of you are going to come back tomorrow and say, okay, it's fine and dandy when you lead me through it, Mrs. Sargent, but now you want me to do it on my own? That's my struggle. And that's why we're just going to keep practicing. Okay, that's why I spend several days with this lesson just practicing. And that's why it is important that you go home and attempt the homework tonight. And I'm going to say attempt every single problem in the homework tonight. Just don't, man, I got frustrated on the second problem, Mrs. Sargent, so I quit. You have to, work your way through it. Now, am I saying you can do every single problem tonight in homework? I mean, technically you are capable based on based on the information I provided. But am I saying every single problem is going to make sense to you tonight? No, not necessarily. So, but this is where we have, you have to give me the effort of trying outside of class so that when we come back, some of it will start clicking the more we do these. Okay? That's the best I can suggest here. Okay. Am I safe to move on to C or not? Everyone's got their questions answered. Everyone knows how we did everything. Okay. So C is cosine x over 1 minus sine x over cosine x. Two fractions being added or subtracted. Likely to try a common denominator. Okay? So, let me see here. First of all, I'm going to write. Oops, wrote it a little too small, but I'm going to write common denominator here. What is the common denominator here?
Oh, isn't it just cosine?
You need 1 minus sine x cosine x. You just multiply what doesn't have the other one.
Yeah. Here's my side note for a moment. What if this was, say, I'm going basic here. What if this was for those of you that struggle with fractions, okay, that's who this is for. If this was 1/5 plus 1/2, what would your common denominator be? 10. And why is it 10? Because 2 times 5 is 10, yes? They have nothing in common, so you just multiply the denominators. So what is my common denominator here? They have nothing in common, so you just multiply the denominators. Does that make sense? Huh? I don't understand.
Identities. Like, is there going to be a situation where we can get a common one where we can actually subtract them?
Oh, I don't know. Okay, so common denominator is 1 minus sine x times cosine x, correct? And I'm setting myself up to go ahead and write this all as one fraction. Now, as I look at my first fraction in the denominator, what am I missing in the denominator of the first fraction? I currently have a denominator of 1 minus sine x. I'm looking for a common denominator of 1 minus sine x times cosine x, so I'm missing cosine x. So that means this first fraction has to multiply by cosine x. What do I do to the denominator? We do to the numerator. What is, in the numerator, cosine x times cosine x? Cosine squared x for my first fraction. Okay, then the second fraction. Here's my minus sign because I'm subtracting the two pieces, yes? My second fraction currently has a denominator of cosine x. What is it missing from the common denominator? It's missing 1 minus sine x. What do I multiply the denominator by? You multiply the numerator by. Which means I'm going to be multiplying, I think we'll do this in the next step. What am I going to be multiplying? Sine x times 1 minus sine x. Sorry, I'm realizing I feel like I'm already possibly doing too many steps together by going ahead and putting it together as one fraction. So I'm going to do this next step. Are we okay with what I have right here? Not 100% sold. And I think what it comes down to here, guys, my denominator is, if I go back to this one, 2 times 5, yes? So what would you have to do with the first fraction? Multiply by 2. So what would it be here? It would be 2 times 1. Plus, what do you have to do with the second fraction? Multiply by 5. So it'd be 1 times 5. So it's kind of like me writing it out as that step before I actually simplify it.
We're going back to 4.
If only we could go back to when we first learned fractions, right? You guys really want to go back to the end of elementary, beginning of middle school, though? Okay. Continuing along before I run out of time. Okay, so let's start by cleaning up this numerator, which means cosine squared x is cosine squared x. How do we multiply sine x times 1 minus sine x? FOIL, or distribute. Okay, so now, this is a minus sine x, right? What's minus sine x times 1? Minus sine x. What's minus sine x times minus sine x?
Sine squared.
Sine times sine is going to be sine squared. The denominator, it's a 50-50 shot, whether you want to multiply those together or leave them separately. It depends on the problem. Sometimes you'll want to leave them separate because something will cancel later. Sometimes you'll want to multiply them together because you need to. I tend to leave my denominator in pieces until I see what's going on. How's that for an answer? Okay? Now, That numerator. Do you see any pieces you might be able to join together to make something else? Not pieces that add together, so to speak, but pieces that combine to form a certain identity.
I see cosine squared x and I see sine squared. Because you can rearrange it where it's negative sine x plus cosine x plus sine x.
Okay, so, yeah. Okay, what I'm trying to lead you to, since some of you are seeing it, is Pythagorean identity here. Okay, hold on, you're too many steps ahead of me. Now, you could, right here, some of you would be comfortable with this. Oh, it's a cosine squared x plus sine squared x. That's going to be replaced with a 1. And you can do it right here. If you need to physically see this, all I'm going to say is you can rearrange these. If I rearrange this and still say it's cosine squared x, and then sine squared x, and just bump that minus sine x to the end, then you can physically see the Pythagorean identity. And I'm going with some of you need that physical, I see it. Some of you were like, oh, okay, I saw where we were going. But the idea here is I just rearrange that. And now that you see cosine squared plus sine squared x sitting next to each other, is it more obvious? That's my hope there. Is that cosine squared x plus sine squared x, you can see that is a Pythagorean identity. I tend to write PI for Pythagorean identity. So when you see me write PI, realize I'm saying Pythagorean identity. And that Pythagorean identity is 1. According to our identity list, right? So now we have 1 minus sine x over 1 minus sine x times cosine x. Now you have to cancel whole factors, right? In the denominator, I have a factor of 1 minus sine x. In the numerator, I don't have any factors, but the whole thing can be considered a factor. So cancel, cancel. Doesn't equal cosine x, equals 1 over cosine x, because cosine x is in the denominator. So it's 1 over cosine x, which is secant x.
I will never figure it out that by myself.
And that's why we're going to do lots of practice. You are not alone. Okay. You are not alone if you're saying, okay, figuring this out on my own is going to be difficult. I can guarantee you're not alone. You're probably more in the majority right now than the minority. But I'm going to go with you get most of the credit. The question was, what happens if you stop at 1 over cosine x? Yeah, and that I did write it in because I feel like that's more of a, obvious one. But okay, real quick. Let's try and look at E. I am right in the center. Okay. First of all, don't ask. Who knows? E. I'm on time. I see negatives. Flip over to your identities. Where did we have negative x's or negative thetas? So we need to look at our list and see what our even odd identities do for us. Tangent of negative x, according to our even odd list, is equal to what? Negative tangent x. Times cosine of negative x is equal to what according to our even odd identities? Positive cosine x. Sine of negative x is equal to what according to our even odd identities? Negative sine x. Okay, that last one. Pi over 2 minus x. Your brain is saying? That one list that you don't know what it's called. Co-functions. Because confusing ones, whatever. But when you flip the page, you can see co-function as the title, right? Pi over 2 secant of pi over 2 minus x is cosecant. And that's what I'm writing down right now. Now, while I get my screen back, we have what? 4 trig functions being multiplied, yes? They can clean up. Thoughts on what I can do here to clean these guys up? How about we change them all to sines and cosines? Tangent in terms of sine and cosine. Sine over cosine according to our quotient identity. What is cosine in terms of sine and cosine? Cosine. Now, let me ask, what is cosine as a fraction? Cosine over 1? And I'm just doing that because, can you see where we're looking for fractions? What is negative sine as a fraction? Negative sine x over 1. What is cosecant in terms of sine and cosine?
Which is 1 over sine.
Cosecant is reciprocal of sine. So this is 1 over sine x. Okay. Let's see. A negative times a negative is going to make my answer positive. A cosine on bottom cancels with a cosine on top. A sine on bottom cancels with a sine on top, leaving me with a single sine x. Now, that's one where, to me, that one's a little easier. I saw the negatives in the parentheses. I said, oh, even odds. I saw the pi over 2 minus the variable, and I said, oh, cofunction. So there's doableness there. Okay, your homework to go through for tomorrow is page 410, 1 through 37 odds, which means you know right away if you got the answer correct, right? Now, do I expect you to possibly walk in with some blank tomorrow? Well, let me define blank. Should you at least write the problem down? Write the problem down. See, try some stuff. See what happens. I'll be honest. You know what we're probably going to spend all period tomorrow doing? Questions. Okay? I'm being upfront with you here. So, but you have to do your part and give me the effort. Hold on a second. Yeah.